Let's look at this example for optimization. Write down the problem. Example. Find 3 positive integers x, y, and z. So that the sum is 30 and the sum of the squares is a minimum. Okay, all right, so we're looking for 3 integers satisfying these 2 conditions. So let's write it down. We have x plus y plus z equal to 30, and if we call a function that describes the sum of the squares, that will be this, right? Okay, and we're looking for the minimum of this function value f. Okay, but according to the constraint x plus y plus z equal to 30, we can actually just write the function f of x, y, z in terms of x, y only. That would be x squared plus y squared plus 30 minus x minus y squared, because z is equal to 30 minus x minus y, like that. Okay, so now we look for a minimum. Okay, so then we apply the same process. We look for critical points and we justify this does give us minimum. So set df dx, which is 2x plus 230 minus x minus y, and then derivative inner function is -1 equal to 0. df dy is this 2y plus 2 times 30 minus x minus y times derivative inner function, that is another -1. Okay, so simplify this a little bit, we get df dx equals 2x minus -x, so that's 4x. Okay, alright, this is a little bit hard to read, so let me just combine the negative sign a little bit, so then it's an easier read for us. 2x minus 2 times 30 minus x minus y, and this is 2y minus 2, 30 minus x minus y equal to 0. Okay, so we have 2x minus -2x, so that's a 4x, plus 2y minus 60 equal to 0. df dy is 2y minus 2 -y, so that's a 4y plus 2x minus 60 equal to 0. All right, so now we solve for x and y. So let me do 1 times 2 minus equation 2. So what do we have? 8x plus 4y minus 120 minus 4y plus 2x minus 60. Okay, so let's see what we get. With 4y cancels the 4y here, and then this is 6x minus negative negative, so minus 60 equal to 0, which tells us x is equal to 10. Okay, so plug it back into let's say equation 1. What do we have? 40 plus 2y minus 60 equal to 0. Therefore, you do get y equals 10. Okay? All right. So now we have a critical point. So far we have a critical point where x and y are equal to 10 and 10. But we need to justify the second partial derivative test to justify we have a minimum. Okay, so remember this is our function. Okay, with partial derivatives here. Okay, so we now go ahead and compute the second partial derivatives. So fxx is equal to 4, fxy is equal to 2, fyy is equal to 4. Alright, so then the discriminant is the determinant of this 2 by 2 matrix. So that's 4, 2, 2, 4, which is equal to 16 minus 4. Okay, so this happens to be a constant, but in general this discriminant will be a function, okay, because your second derivatives could be function of x and y. We just happen to have a special case where they are all just constants. All right, so here we know that at the critical point d is positive. When d is positive, we also look at what happens to the second derivative of xx, and this also is a positive number. So therefore, the second derivative test tells us that we have a minimum value at 10, 10. Okay, but remember our goal is to look for x, y, z so that the x squared plus y squared plus z squared is a minimum. Okay, so we need to also find the z value. Z is equal to 30 minus x minus y, so that is 30 minus 10 minus 10, which is another 10. So the answer is all the three numbers are 10. Okay, so the set of numbers gives a mean of x squared plus y squared plus z squared, and they satisfy x plus y plus z equal to 30. All right.